Okay, this is chapter 6 homework. It says light from the sun takes about 8 minutes to travel to the earth. How far away is the sun? Know that the speed of light in a vacuum is 3 times 10 to the 8th meters per second. That's on your equation sheet. And in general, it travels at a constant speed, so the speed is the distance over the time. We want to know how far away is the sun. It takes 8 minutes, so I just solve this for d is equal to the velocity times the time. That's 3 times 10 to the 8th meters per second times 8 minutes, but I need to convert minutes into seconds. There are 60 seconds in 1 minute. And so that gives me the time of, or the distance rather, of 1.4 times 10 to the 11th meters. This is sort of a good number to know that light takes 8 minutes. That way if the sun ever dies, we'll at least have 8 minutes to, say goodbye. Light is incident on a set of mirrors that are at right angles to one another. The initial angle of incidence is 30 degrees with respect to the first mirror. What are the incident and reflected angles of the light ray on the second mirror? How high does the ray strike the second mirror? So I know that this angle right here is 30 degrees, and so my reflected angle is also going to be 30 degrees. Right? If that angle is 30 degrees, that means that this angle is 60 degrees. And if that angle is 60 degrees, that means that this angle is 30 degrees. And so my new incident angle is going to be 60 degrees. And then the reflected angle is also going to be 60 degrees. Alright, so that's the first part. What are the incident and reflected angles for part A? Theta I is equal to theta R, and they're both equal to 60 degrees. Now, how high up does the ray strike the second mirror? I want to know this distance. Alright, so I can just draw my little triangle. So I'll draw it down here. Draw my triangle. This is 60 degrees. I have 1.3 meters, and I want to know this distance. The tangent of 60 is opposite over adjacent. That's y over 1.3. So y is equal to tan of 60 times 1.3, which is 2.3 meters. So those are our answers. You shine a laser through water, which has an index of 1.3, as in this figure. The laser beam leaves the water, travels in air, and strikes the wall at some distance y from the floor. What is this height y? So when this comes out, when this light ray comes out, it's going to refract so that it bends away from the normal. Alright, so I want to know then what is this distance. Actually no, I want to know what is the total distance down to the ground. Okay, so this is a lot of geometry. We just need to work through this. So I know this angle is 60 degrees. So this angle is going to be 30 degrees. That's my incident angle. So my first step is going to be, what is my refracted angle? So I can solve that with the law of refraction. I say n1 sine theta 1 equals n2 sine theta 2. n1 is equal to 1.3. n2 is for air. That's equal to 1. So I have 1.3 sine of 30 equals 1 times the sine of theta 2, where this is my theta 2. That's my refracted angle. And solving that for theta 2, the inverse sine of 1.3 sine of 30 divided by 1. That gives me an angle of 41 degrees. 41 degrees. So this angle is 41 degrees. That means that this angle is 49 degrees, because 90 minus 41 is equal to 49. Okay? Now, similarly, I need to find out what is this distance. In order to find that distance, I'm going to need to find this distance. Okay? In order to find that distance, I need to find this distance. I'll call this x1. I'll call this x2. I'm going to call this y2, and then we'll call this y1. Alright, and what we're looking for is y in the end, and that's going to equal y1 plus y2. That's going to be our final solution. But in order to find y2, we need to find x2. In order to find x2, we need to find x1. So, let's find x1. Draw a line here. x1. I have a triangle. This is x1. This is 60. And this is 0.75 meters. So the tan of 60 is 0.75 over x1, and x1 is equal to 0.43. Alright, that means that x2 is equal to 1.3 minus 0.43, which is 0.87. Now I can find y2. I have a triangle. This angle is 49 degrees. I have 0.87 here, and I need to know y2. Again, tangent of 49 is y2 over 0.87. So y2 is equal to 1 meter. Alright, so now my answer is going to be 0.75 plus 1 is equal to 1.75 meters. That's the final answer. The distance from here to here is 1.75 meters. Alright, number 4. Light is incident, normal to a 1 centimeter layer of water that lies on top of a flat lucite plate with a thickness of 0.5 centimeters. How much more time is required for light to pass through this double layer than is required the same distance in air? And there's the index for lucite. So we have two instances. In the first case, we have light traveling through a layer of water. That's my water. And then a layer of lucite. That's my lucite. The index, this is my water. And this is my lucite. So I have this light traveling through both of those. This distance is 1 centimeter. And this distance is 0.5 centimeters. In my other case, I have light traveling the same distance, but it's all in air. So this distance is 1.5 centimeters. 1.5 centimeters. So now I want to find the time required for the light to travel through each of the substances. And in that case, I need to know what is the speed in each of the substances. And I can find that because the speed of light traveling through a medium is equal to c divided by the index of refraction. So when light travels through water, it slows down by a factor of 1 over the index of refraction. So let's find the time required to travel through water. Is going to be the distance over the speed. So that's meters over meters per second, which gives me seconds. That's going to be 0.01 meters, 1 centimeter, divided by 3 times 10 to the 8th, divided by 1.3. Yeah. And that gives me the time required to travel through the water, which is 4.3 times 10 to the minus 11 seconds. And now the time required to travel through the lucite is d over v. That's 0.005 meters divided by the speed of light in a vacuum divided by 1.59. And that gives me the time required to travel through the lucite. It travels slower through the lucite, but you have less distance, so it's 2.65 times 10 to the minus 11 seconds. And so the total time is the sum of these two, 4.3 plus 2.65. That's 7 times 10 to the minus 11 seconds. That would be, 70 picoseconds. Now, let's look at this opposite side. For air, The time is the distance over the speed, which is going to be 0.015 meters divided by 3 times 10 to the 8th meters per second. We generally assume that the index of refraction for air is 1. It's not entirely true. The index of refraction for a vacuum is 1. The index of refraction of air is slightly more, but we'll just assume that it's 1 in this case. So that's 0.015 over 3 times 10 to the 8th, and it's 5 times 10 to the minus 11 seconds. So our difference in time is that in this scenario on the left, it requires 2 times 10 to the minus 11 seconds more than for the light to travel the same distance through air. So a small but measurable change in time. Alright, a ray of light strikes a flat 2 centimeter thick block of glass with an angle of 30 degrees with the normal. Trace the light beam through the glass and find the angles of incidence and refraction at each surface. Alright, so in this case it's moving from a low index to a high index of refraction. So it's going to bend towards the normal, and then here it's going to bend away from the normal. Alright, we want to know the angles of incidence and refraction at each surface. So I want to know this angle, and this angle. Alright, I'll call this theta 1, theta 2, and theta 3. Alright, to find theta 1, I say n1 sine of 30 equals n2 sine of theta 1. And n1 is equal to 1. For glass, it's 1.5 sine of theta 1. And so theta 1, that is my refracted angle inside of the glass, is 19.5 degrees. And then I'm basically done, because theta 1 and theta 2 are going to equal. Theta 1 equals theta 2. Alright? Like if I look at this, remember geometry? If I have two lines and I run a line through it, then, well, that's not a very good example. Let me show you another example. Let's say, oh no, that's a fine example. So if never mind. These two angles are equal. Theta 1 and theta 2 are equal. Likewise, theta 3 is equal to 30 degrees. All right, and you can see that because since you know that theta 2 is equal to 19.5, you can say that 1.5 times the sine of 19.5 is equal to 1 times the sine of theta. And if you just do that math, you find that theta is equal to 30 degrees. So when it comes back out into the new medium of air, it returns back to the original incident angle of 30 degrees. Right, the index of refraction for red light and water is 1.331, and for blue light it's 1.34. If a ray of white light enters the water at an angle of incidence of 83, what are the underwater angles of refraction for the blue and red components? So I have light going from air to water. Air to water. These rays of light are going to split into their blue and their red components. The blue light, which has, for this case, the water has a greater index of refraction for the blue light, so the blue light is going to bend more than the red light. So the blue light will look like this, and the red light will look like this. Alright, I want to measure what are these angles for the blue and for the red light. I want to calculate what are those angles. So this is similar to what we've done before, but for the blue, we say 1, that's the index of refraction for air, times the sine of the incident angle, which is 83 degrees, is equal to 1.34, that's the index of refraction for blue light, times the sine of theta. And then solving for theta, I find that theta is 47.79 degrees, keeping 4 sig figs because that's what I have throughout. And then for red, I do a similar thing, 1 sine of 83 is equal to 1.331. That's the index for red light in water times the sine of theta. Solving for theta, 48.22 degrees. So you see the red has a greater refracted angle, but that means that it's bent less. It's bent less, but it has a greater refracted angle. So it's more like the incident ray. Alright, a certain kind of glass has an index of refraction of 1.65. Let's see, this is practically the same as number 6. You have white light that travels from air to glass. From air to glass, it has an angle of 30 degrees, an incident angle of 30 degrees. The air has an index of refraction of 1. The glass has indices of refraction that are different for blue and red. For blue, it is 1.65. For red, it is 1.615. Alright, so the blue is going to bend more, just like before. Blue will look like this. Red will look like this. In this case, they're asking what is the angle between the two beams inside the glass. So I want to find the difference between this angle and this angle. But again, I have to find theta for blue and theta for red, and then just take the difference between them. So in order to do this, I say 1 sine of 30 equals 1.65 sine of theta. That's for the blue. And that theta is equal to 17.6 degrees. And then for the red, I say 1 sine of 30 is equal to 1.615 times the sine of theta. And I solve for theta, and theta is 18 degrees. And so my change in theta is 18 minus 17.6, which is equal to 0.4 degrees. And that's your answer. Calculate the critical angles for the following materials. Let's see, I made a change in this because you don't have these indices of refraction. I made it, instead of for zircon, I made it for glass. And instead of fluorite, I made it for diamond. There's a table in your book that has these indices of refraction. I just want to know the critical angle. Remember, the critical angle occurs when I have light that is traveling inside a medium. And this critical angle, which is going to be this angle that we'll measure, occurs when the refracted light is at 90 degrees. So the refracted light is at 90 degrees. So we're basically saying theta R is 90 degrees. Alright, so I can say N1 is N1 sine theta critical is equal to N2 sine of 90, and of course the sine of 90 degrees is just equal to 1, so that goes away. Alright, so if I solve this for theta critical, it's going to equal the inverse sine of, what's that? N2 over N1. N2 over N1, and N2 is going to be air. So I have the light traveling from the material, glass, diamond, or ice, into air. And so I want to calculate the critical angle for each of those. For glass, N is equal to 1.52, and so theta critical is the inverse sine of 1 over 1.52. It's equal to 41 degrees. For diamond, N is equal to, it's pretty big actually, 2.42, and so theta critical is the inverse sine of 1 over 2.42, which is 24 degrees. And then for ice, N equals, in your table, 1.309. And so my theta critical, I'll just give you the number here, is 49 degrees. Please note that if instead, let's say for example, let me write over here on the side. Let's say instead of going from, say, glass to air, I was going from air to glass. So I had a light ray that was coming in this case. All right. In order to have a critical angle, you have to be moving from a high index of refraction to a low index of refraction in order for your refracted ray to refract away from the axis. So if you're moving from air to glass, there is no critical angle because the light ray is just going to get closer to the axis. It's not going to move away from the axis. So in a case of moving from low N to high N, there is no critical angle. And you know, if you put it in your calculator, if you try to do, say, the inverse sine of, let's see, what is it for glass? 1.52 over 1. That's going to give you an error because it doesn't exist. There is no critical angle if you're moving from a low index to a high index. That's why fiber optics, they have a high index material surrounded by a low index material, which can be air, but usually it's not. Usually it's some other plastic. That's great. That's the end.